right, so let's get started. Today is lab 4. It's on centripetal force. Does anybody know what centripetal force is? You guys covered this yet? No, okay, so I'll be introducing it then. So centripetal force has to do with the force that an object feels while it's going in circular motion. So here I have an object, it has mass, and it's going to be going with a constant speed in this direction. This is its velocity vector. And in order to stay on its path, we have to apply a force to it. So there's a force usually by a string or something attached to it in this direction. We call that the centripetal force or centripetal force. A quick note is this is not the centrifugal force. Centrifugal force is something different. It has to do with non-inertial frames, or the, how do you guys say it? I can't even say it. Centrifugal. I don't even know what that is. So that's just like a made-up term that people say. I don't know. I know what centrifugal is. Physically, I don't know what a centrifugal force is. All right? So if you say that, I might look weird at you, like I don't know what you're talking about. But I do accept centripetal or centripetal. Okay? So either one of those is fine. All right. So let's call this r. It's the distance from the radius from the center to the mass. And what's going to happen if the mass is, say, over here at some time later? Is it still in motion? What do you think? Yes? No? Maybe? If you're spinning it, yeah, it's still in motion. So it has some speed, but now the speed has changed directions. So my question to you guys is, has the object accelerated from this point to this point? Yes, it has. Why? Because it changed directions, okay? So its magnitude of its velocity vector, its speed was constant, but its velocity vector changed direction, so therefore it accelerated. And it accelerated towards the direction of the force, which is, which direction? Towards the center of the circle, or radially inward is another way of saying that. So it's always towards the center, so it still experiences a centripetal force inward. Is this okay? Everybody good with this? All right, so let's talk about that force. Centripetal force. What do you think it depends on? The centripetal force. What are some parameters or variables that might affect how big that force is? Good, the mass. It's proportional to the mass. You double the mass, you double the force. So if I doubled this mass and I spun it around the same circle, everything else constant, same circle, it would have to do twice as much force because it's twice as massive. What else might it depend on? The acceleration, yes. More specifically, though, something else? Anything? Right. I'm trying to get you guys to say how big the circle is, right? If it's a bigger circle, you need less force, right? You guys have all played that game as kids, like when you grab each other's hands and you spin around and the guy, right.
The one where people can dislocate their shoulders?
Yes, that one. All right, and it turns out it also depends on the velocity, but it depends on it in a way that you guys might not realize, which is v squared. So that's the centripetal force. And since F equals ma, you can do the centripetal acceleration as just v squared over r. Any questions so far? All right, so if we want to know the centripetal force or the acceleration, either one, they're just proportional by the mass, we need to know the radius of the circle, which isn't so bad. We can just get out a ruler and measure it, right? And we need to know the velocity. How do we determine the velocity of the object? All right, so he's saying that basically the definition of velocity is the change in x, I think is what you're saying, right, over the change in time. And what is the change in x here? How much is x changing? Well, for one revolution, it's one circumference of the circle. So delta x would be 2 pi r, the circumference of the circle. Circumference, missing an f somewhere. So that's 2 pi r, as you guys remember. And then how long does it take to go around the circle? 1 period. So delta t, we use capital T for the period. Circumference. All right, any questions so far? So I'm just going to plug this into the velocity. I get 2 pi r over big T. So in order to determine the velocity, all we have to do is know r, and then we have to measure the time it takes to go one circumference, 1 period. So that's something we can measure. So let's go ahead and plug this velocity into this guy here. Can we simplify? Catch me if I make a mistake. It's a lot harder to do this on the board than on paper. I think that's right? All right, so this is the centripetal force as a function of mass, the radius of the circle, and the period, but you guys didn't catch me. I was testing you guys. All right. I'm going to box this. All right, so if we were to graph maybe the centripetal force versus mass, what would the plot look like? If I double the mass, what happens to the centripetal force? It doubles too. So as I increase the mass, what happens to the force? Linear. It's linearly proportional. If I double the radius, what happens to the centripetal force? It doubles too, right? So it's also linear proportional. And that's how you break your arm, you dislocate your shoulder. All right, so the last one is T, or the period. How does the period and the centripetal force depend on each other? Inverse squared, right? So this is kind of like Newton's gravity. So it looks something like this. So as T gets very large, the centripetal force gets very small. As T gets large, the centripetal force gets very small. And if you have a very, very short period, that means you're spinning it really fast, right? Like a centrifuge. The centripetal force gets very large. All right, any questions? All right, so you have the apparatus here where you guys are going to do this experiment. It's kind of wonky, but it works pretty well. So over here we have a spring, and this is gonna, you're gonna calibrate the spring by hanging a weight off of at the end of here. So the weight is gonna hang off the end of here, so you know mg, which is the force. It's gonna pull that down, and then you're gonna adjust this guy to match wherever the bright thing is. All right, then you're gonna take the hanging weight off. And it's gonna do what I did here, and then you're gonna spin it. And it's really important to take the hanging weight off before you spin, okay? And you guys laugh, but I've had this done multiple times where people hang the weight and they spin it, and then the weight, like, you know, fleeing everywhere. So something like this. All right, you see the bob went down, the spring is stretched. That's because it feels a force, and that force is the, help me out, centripetal force, okay? Not the centrifugal force or the, how do you guys say it?
I think it's just somebody saying it the wrong way.
Centrifugal. It's not centrifugal, okay? So it's hard to break the habit. I guess when you were a little kid, somebody said it and it stuck. Disney Channel ruined you guys. All right, so it's kind of fun to spin this. So you can just kind of do this all day. All right, and so someone's going to keep it spinning, you know, and you want to keep the bob, like, you know, where you marked it, because that's when you know the centripetal force is equal to the force of the weight that you hang on, the calibration weight. And then you're going to, someone's going to time it, so your partner will time it. What you want to do is you're going to count 10 revolutions, so 10 periods. And you're going to time how long that takes. Why 10? Anybody know why we picked 10? Why not one period, one revolution? Because it's too short, right? It's really inaccurate. Like, it only takes like a little over a second. So if you do 10 and you divide by 10, you average it out, so you get a good number, okay? That's why you do 10. And it's very important, if you don't want 10% error in your data, that when you start counting your revolutions, that you start at 0, 1, 2, 3. Okay, some people like to start at 1, but then you're only really counting 9 revolutions. Hopefully that makes sense to all of you guys. So what are we going to change here? So we can change what? We can change the radius. So we can adjust this guy. And we can see how the centripetal force depends on the radius. Okay, that's that graph. We can change what else? Yes, we can change the mass, which is this mass, by the way. I forget what they call it. We change it like every year because there's two masses in this experiment, right? There's the calibration weight, I think we call it, and then there's, I think we call hanging mass. So this is the mass for this guy. I think they call it capital M too. So I use little m, but so this is the mass you're changing. You're adding mass to this guy, and then you're doing this type of plot. And the last thing, obviously, you can change is what? The period, right? How do we change the period? I'm trying to remember. I think we change it indirectly. We change the calibration. We change the calibration weight, so we calibrate it to different centripetal forces. So really, we're varying this guy. Okay. All right. If there's any questions, I mean, feel free to ask me. You know, sometimes setting this up is a little bit confusing, you know, especially if you're reading the lab manual and trying to understand the words that they say, and we change the words every year, so even I get confused sometimes. But the important thing is to know sort of these type of graphs. And those are basically what you're trying to make. I think the last graph is not this graph, though. I think it's, they make everything linear. No, so they plot versus 1 over t squared, so it's in linear. But it's the same idea, right? So 1 over t squared is linearly proportional. All right, so that's it. You guys can get started.